Welcome back, Professor Bright here, and we are going to look at a new type of function called a rational function. We just finished discussing polynomial functions, and so rational functions build off of all that, where it is literally just a ratio of two polynomial functions. So p of x and q of x are two polynomial functions. We just have to add the condition that the denominator is not 0. And so then we create a new function, rational function, called f. And so just as a quick example, we could have something like f of x is equal to x plus 1 over x minus 1. That is a rational function. We could also have g of x equaling x squared minus 2 over x squared plus 4x plus 3. Both of those are polynomial functions. And then we would just have to say, we can't have these values in order for the function to be defined. Something that is not a rational function would be something like h of x, where we have, say, square root of x all plus 1 over x plus 1, right? The square root is not a polynomial function, okay? If we had also something like j of x that is, 2 to the x all over x squared plus 1. Again, 2 to the x, that's an exponential function, which we'll see later, but that ends up not being a rational function either. Okay, now when you see these functions and the fraction appearing, if that gives you pause and you're a little concerned, I encourage you to go back into the slides, the PDF version, and first of all, always review the learning target and learning steps, but then later on at the end of the cover page, you'll notice the bottom has a bunch of videos that you can review just on, the algebra related to working with rational expressions. And then it also has sample exercises and solutions for those. But for now, we're going to say we're solid on that, and we are going to continue our study of rational functions. And so you've actually seen these before, right? We have seen these pop up when we were talking about finding a domain of a function. We just didn't call them rational functions earlier. We just wanted to make sure that we were looking and finding a domain for the function that we were working with. So we knew that in expressions like f, we had to take x minus 1 and set it not equal to 0 in order for the function to be defined, right? And so we would, then say x can't be 1, and that would lead to our domain using interval notation. Okay, so we kind of know this skill already. Let's go ahead and try it. Okay, so in f, here to find the domain, I would just take the denominator and say that this cannot be 0. So then on a number line, I would just have a hole at 0, but I could allow for every other value to occur. So then writing out the domain, I'd have negative infinity to 0, union 0 to infinity. And you're like, oh gosh, this is old hat. Yep, should be. Okay, that's intentional. Going on to g, we would do the same thing. T squared plus 1 not equals 0. T squared cannot be negative 1, and that is never true. So then, like, it's not possible to square a number and get out negative 1. And so we would just say that the domain is all real numbers, also known as negative infinity to infinity. For h of z, okay, again, to find the domain for this function, I would take 2z squared minus 7z plus 6 and set that not equal to 0. Okay, just saying I can't have 0, or you could set it equal to 0 and remove it, tomato, tomato. And so we just finished finding zeros of polynomial functions too. So one way in which to find the zeros was to try factoring. I'm going to try that. Let's see if that gives me anything. 2z and z would multiply to give me z squared. And then two numbers that multiply to 6. Oh, I don't know. Let's try 3 and 1. And they need to give me negative 7 when I add them. So let's see if I distribute here in my head. 2z squared minus 3 or minus 6z and then minus another z. Okay, that would give me 7z. And then if I multiply, that does not give me negative 6 though, or positive 6. Okay, well, so this would need to be, let's see, how about a 2 and a 3? Let's see, so if I had a 2 there, that would have given me 8. But maybe if I flip them around, let's try a 2 here and a 3 there. So then I'd get minus 4z minus 3 more z, so minus 7z. This would work. Okay, so this is the factorization. And then I'd set each factor individually equal to 0. So 2z minus 3 equals 0. And then z minus 2 not equal to 0, not equal to 0 rather, and then solve, add 3, divide by 2, z cannot be 3/2, and z cannot be 2. So then I could put these on a number line, but the short of the long story is the domain would be -infinity to 3/2 union 3/2 to 2 union 2 to infinity. Okay. Now these values that I ended up taking out of the domain of all real numbers, these actually have a special name for us. They're called poles, like North Pole or South Pole, right? And they're just the values that make the denominator 0. Okay, so you could say a part of finding the domain is to find the poles, remove the poles from all real numbers. That's effectively what we'd need to do to state the domain of a rational function. Okay, so the poles for each of the above functions are, and I'm just going to kind of go down here, x equals 0 would be the pole for the first function, none for the second one, and then over here for the third one, we just saw that that's 3/2 and 2. Okay, so each of these poles is going to be expanded upon further, but we, for now, are just going to leave them for this video. Okay, so in all, this video, we introduce ourselves to rational functions, just ratio polynomial functions. We found the domain of each of the rational functions we had here and recognize that the values that we removed from the domain are called poles. We have terminology for them now. Next video, we're going to work on classifying what happens at each one of these poles.